Welcome to a new session on deadlock handling. Till now what we have done is we have talked about processes, and we have talked about process synchronization, and while talking about a process synchronization we had talked about various approaches. So the approaches which we had seen for handling the process synchronizations were software approach. Then we had seen a hardware approach where we talk about enabling and disabling of interrupts, and then we did discuss something about a special instruction supported by the microprocessor, and then we saw something about operating system support for handling the process synchronization, and that was we discussed about semaphores. We did discuss about monitors and message passing. In entire discussions pertaining to the process synchronization, we had essentially seen that that the problem arises because the processes are going to be competing, and the amount of resources which are going to be there in the system are going to be finite, and the resources, some of the resources are going to be non-shareable resources. So under all these conditions we have found that whenever synchronization is required to be achieved, there are three important things which are required to be carried out. The one being a mutual exclusion, and we have seen how the mutual exclusion can be achieved. The various approaches which has been discussed for a process synchronization they give you a fairly good idea that how the mutual exclusion is going to be achieved. That is the first and foremost task of a process synchronization, and because of such a requirement, what happened that at a time any solution which is proposed for a process synchronization, we have seen that it can lead to two different kind of a problem. The one is a one is a starvation, the issue of a starvation. So again the starvation can be prevented by suitably designing the solution, process synchronization solution, but the last problem which is faced is a deadlock problem, and we will try to focus in this particular session that define what the deadlock is, and we will try to see that what are the various approaches for handling the deadlocks are. Let us see that what a deadlock is. So we say that a set of blocked processes could be there which are holding a resource and waiting to acquire a resource held by another process. Let us for an example, that if suppose we have a system which has only 2 tape drives, and there are two different processes which want to simultaneously access both the tape drives. So let us say that if we look at a program which is going to be there. So let us say that these tape drives are guarded with the help of a semaphore variables. So there are 2 tape drives, namely say tape drive A, tape drive B, and they are guarded by semaphore variable 1. So process P0 could be something like this, that wait A, wait B, meaning to say it will go and execute a wait on a semaphore variable A. If the value of A is 1, so it will get decremented to 0, and the process would continue, go to the next statement, execute the wait B. If the value is 1, then it will get decremented to 0, and since it is non-negative, it will continue to move further. That essentially means that so this can be for a process P0, and let us say that for a process P1 the code is something like this. Now under this scenario, let us assume that process P0 comes and it executes the instruction wait A. So it acquires the tape A, and then after it has acquired a tape A, let us assume that process P0 gets suspended and P1 comes, and it executes the wait B. So that is, it acquires the tape B. Now what happens? Now any one of these processes, if they try to execute the next instruction, they are going to get blocked. So eventually we can see that process P0, when it will execute a wait B, it will get blocked, and process P1, whenever it will execute wait A, it will get blocked. Now both the processes are in a blocked state, and the process P0 would be waiting for tape B, and process P1 will be waiting for a tape A. And what has happened? P0 is holding a tape A and waiting for a tape B, which is held by process P1, and similarly a process P1 is holding a tape B and it is waiting for a tape A, which is held by P0. So whenever such a scenario occurs, we find that both the processes are going to be suspended or stalled, and they will not be able to progress. We call such a scenario, such a case, that these two processes are in deadlock condition. Let us see the same thing with the help of another illustrative example. So we are saying that we have a road where there is going to be a number of vehicles which are there. So and then there is a bridge connecting these two roads. So roads can be considered as a as a resources. So there are set of vehicles on this side of a road which are there, which are using this resource. There are set of vehicles which are here on this, and the condition here is that the traffic, because of the size of a bridge, the traffic can only flow in one direction. So what happens, that let us say that if suppose this constraint is not followed, then in that case we find that a vehicle from this side comes here, and simultaneously a vehicle from this side also comes and moves. So actually we should see that we find that this particular vehicle is occupying a resource and trying to acquire another resource. So now what happens, that these two, so this vehicle comes from this side and it stays here, and this vehicle comes from this side and it stays here. So we find that now there is no way that these vehicles can move further. There is a sort of a traffic jam which occurs here, and there is no way that this traffic jam can be broken. Now let us metaphorically, if such a scenario occurs, then how the traffic jam can be avoided. So the situation is that it can only be avoided where one of the vehicle should reverses and goes back and clears the bridge, right. So in case of a software, what is happening, that if suppose a software has already executed up to a certain point, now we are saying that it should take a step back and go back. That means that whatever it has done till that point of a time, it has to be undone, it has to be rolled back. So, and if there are more number of vehicles, then every vehicle has to roll back in this case. So we find that this is an example where we see that a deadlock occurs, and because of a deadlock, for a recovery from the deadlock, we are seeing that there are issues, that is, issues pertaining to the rollback is required, and even preemption of the resources is required. That when it is rolling back, it is actually meaning that some kind of preemption is taking, when it is taking a step back, it is actually meaning something similar to that resource is being released, for the other person to move on. And we may find that it may not be possible. There may be a resources, usually in case of IOs, what happens that once the IO resource is allocated, IO preemption is not there. It is not allowed. For an example, if you look at a printer, and if suppose process has printed half page, and then another request from another process comes, and that requires the printer, and now assume that the first printing process which had printed half page is preempted. So now when it gets preempted, now when second process starts printing, what happened that half of the page is page information is coming from a process 1, and another half of a page information will come from a process 2. So we find that many a times we can have cases where the preemption of resources may not be possible. And we should also notice that if suppose somehow we say that okay, the resource will get preempted, and so this vehicle will be taken back, then we can very clearly see that this could lead to a starvation, in the sense that now out of these two vehicles, which one should go back? So it is possible that we randomly decide, we say that this is the process which will go back. So now this goes back, and it may just happen that every time when such a condition occurs, only the process, this process is the vehicle on this side of a bridge is asked to go back. As a consequence, it may happen that these vehicles which are standing here will never get a chance to cross the bridge. Till the time all these vehicles are coming from this side of a bridge, this will never get a chance. So if there is a continuous flow of vehicular traffic from a left hand side, then right hand side vehicles will never get a chance. So this is what we call as a starvation. So we find that while we are trying to attempt solving the problem of a deadlock, the solution, any solution proposed for the deadlock could actually result into a starvation as well. So we will see that what the various approaches for deadlock handling are. So before talking about deadlocks, let us start looking at how to model the system. And for modeling the system, we say that any given system would have a set of resources. So let us assume that there are m number of resources named as R1, R2, Rm, and these resources can be anything. Can be CPU cycles, can be memory, can be IO devices, etc. Then it is possible that for each of the resources there can be multiple instances. For an example, there is a possibility that a particular computing machine has more than one hard disk drive. So there are say 2 hard disk drive or 4 hard disk drive. So then we say that we have 4 instances of hard disk. So there can be a resource type Ri, and it can have multiple instances, that is Wi is the number of instances which a resource can have. And a process, whenever the process tries to utilize a resource, what it needs to do, it follows a kind of a protocol. So the protocol is something like the process would need to make a request for the resource, and OS would grant the resource. Once the process has finished the usage of the resource, then process is voluntarily going to release the resource. So this is a kind of a protocol which is followed. So we can say that processes would make a request, and then OS would grant the request by allocating the resource, and as a consequence, we can very clearly also see that when such a thing is happening, then it is the responsibility of the system to keep track of the resources, number of resources and its utilization. So, that is the responsibility of the operating system. And usually what happens that request and release operations are carried out through a kind of software which we call as a system calls. So, whenever a program wishes to use a resource, what it does, it uses a system call. For an example, open. Open is a system call which can be used for opening a file. So, deadlock, we find that the deadlock can arise because of if there are 4 conditions which are responsible for a deadlock occurrence, and all these 4 conditions must hold simultaneously. So, first condition is that mutual exclusion, that is only one process at a time can use a resource, and mutual exclusion is required primarily for the reason that the resource which is being accessed is non-shareable. If resource is shareable, then mutual exclusion is not required. So, in general, we find that the issues are that whenever processors are trying to simultaneously access non-shareable resources, the problem of a process synchronization occur, and for the deadlock to occur, mutual exclusion is one of the conditions. The second condition is hold and wait. That is, there must exist a hold and wait condition in the system. That is, a process is holding a resource and waiting for some other resource to become available. We can very clearly see that if suppose there is a process which is not holding any resources, then it cannot be a part of a deadlock, because it is not holding any resources. It does not require, see, we do not know whether it requires any resources or not, and it may just happen that it does not require any resources, it will just simply execute and get out of the system. So, a process which is not holding any holding any resource cannot be a part of a deadlock. So, for deadlock to occur, the very important condition is hold and wait condition must exist. And let us say that even if suppose the process is holding a resource and waiting for a other resource, so deadlock can actually be avoided if the resource held by a particular process can be preempted. But in general, we have said that it is not in general for a general purpose operating system, the resource preemption is not allowed. We have seen that why the resource preemption cannot be allowed. So the condition is, the another important condition is no preemption. That is, the system follows a convention of a no preemption of a resource, meaning to say once the resource is allocated, it is not forcibly preempted by the operating system. Resource is released voluntarily by the process once the process has completed completed its utilization. So, this is the third condition which must occur, and then first and foremost, the final condition is that circular wait. So, circular wait is something like this, that we say that we have a set of processes, say P0 to Pn, and we say that P0 is waiting for a resource that is held by a P1, and P1 is waiting for a resource which is held by P2, and finally we say that Pn process is waiting for a resource which is held by P0. So, we find that there is some kind of a circular wait which occurs, and because of which each of the process is waiting for a resource which is held by the other, therefore, a deadlock occurs. So for a deadlock, so we say that deadlock can actually be characterized by the 4 conditions, and all these 4 conditions must hold simultaneously, then only the deadlock can occur. Otherwise the deadlock cannot occur in a system. So let us see that how the information inside the system can be maintained, the various approaches which are used for maintaining the information about the resources and processes and resource allocation. We will try to see few approaches here. So one of the approach, one of the commonly, one of the simplest approach which can be used for this purpose is known as a resource allocation graph. And we say that a resource allocation graph consists of a set of vertices V and set of edges that is E, and these vertices are partitioned, or they can be classified in 2 different types. So we call one type, that is a process, that is a, so we say that P is a one set of vertices and vertices, that is a P corresponds to the processes, and R is the another set of vertices that is resources. So we say that if we say that P is the set of processes which are going to be depicted at as a vertices, so I can say that this set has a process P1, P2, Pn. So there are n number of processes, or this P is a set of all the processes in the system which are there, and R is the set of all the resources which are there in the system. So we say that there are n number of processes and m number of resources. So these are the 2 kind of vertices which are present in the system, which we are going to model. And then similarly we have 2 different kind of edges also, because it is a graph. So graph in general we say that graph would have vertices and edges. So here again we classify the edges into a 2 category. One we say a request edge. So request edge is a directed edge, and it is depicted as a PI RJ, and this essentially says this essentially means that process I is making a request for a resource RJ. So this is how the information would be there, that if process Pi is making a request for a resource Rj, this is how it is going to be depicted in the system. And once the operating system allocates the resource, then this request edge could get converted to what we call as a assignment edge. So in that assignment edge again is a directed edge, and here we can see that it will be depicted as a Rj assigned to Pi. So this essentially means that resource Rj has been allocated to process I. Jth resource has been allocated to ith process. Diagrammatically we use a certain symbols. So for a processes in general we use a circle, and then resources we use a rectangle, and inside the rectangle if you see that we have a small rectangles indicating number of small rectangles. So in this case we see that there are 4 rectangles. This is essentially indicative that this particular resource type has 4 instances available in the system. So if this resource is corresponding to a tape, this would essentially means that there are 4 tape drives in the system. And similarly we can how with the help of edges, if we try to model the graph, we would say that Pi is ith process is making a request for jth resource, and in this case this is indicating that jth resource has been allocated to ith process. Let us look at a let us try to see an example that how a resource allocation graph could look like. So from any given resource allocation graph of this kind, there are certain information which we can immediately observe. Just by looking at a graph, we shall be able to say that currently when the snapshot of a system was taken, system had 3 processes, P1, P2, P3, and system had 4 resources, R1, R2, R3, R4. P1 process has been allocated a resource R2 and has paid a request for a resource R1. P2 process has been allocated resource R2 and R1 and is waiting for a resource R3. It had made a request for a resource R3 and and P3 process has been allocated a resource R3. So, and then while talking about resources, we can say that there is a one instance of a resource R1 in the system, there are 3 instances of a resource R2, R3 in the system, and there is only one resource for a R3 in the system. There are 2 instances of R2 resources and there are 3 instances of R4 resources. R4 resources have not been requested by any of the processes and have not been allocated. R2 resources have been allocated to different processes. So, there are lot of information which one can observe, one can gather just by looking at a graph. And let us try to look at this and say that whether from looking at a graph, can we say that if the deadlock is going to occur or not. So, the simple thing is we can do an analysis. This analysis we will continue to follow for every resource allocation graph which we are going to handle. So, let us analyze this particular simple example. So we find that P1 process cannot execute until unless it gets R1. So, it is waiting for a R1. So, until unless R1 process is released, R1 resource is released, P1 will not be able to work, P1 will not finish. Let us come to P2. P2 in general required 3 resources, out of which 2 resources are available to it and it is waiting for another resource, that is it is waiting for R3 resource. So, until unless R3 is made available to P2, P2 will not be able to execute. Now, come to the P3. P3 has been allocated R3 resource and it is not requesting any other resource. So, if it is not requesting any other resource, so please understand, this is a snapshot of a snapshot of a system at a given moment of a time. So, at this moment of a time, by looking at it, if I try to analyze, then I would go something like this, that I know that P3 has been allocated the resource which it has asked for. That would mean that it is a good idea, or it is safe to assume that it is possibly not going to make any more request for the resources. All the resources which it wanted has been allocated. As a consequence, since all resources have been allocated, as a consequence P3 would finish. And once P3 would finish, what happens, that it is going to release the resource R3. Now, when R3 resource becomes available, now operating system can allocate it to process P2, because P2 has been waiting for R3 resource. So, now the R3 resource will get allocated to process P2. As a consequence, P2 process will finish its execution. Now, when P2 finishes its execution, P2 is going to release its resources, that is R1 and R2. Now, R1 is released, so now P1 can execute. So, we find that just by looking at a graph, at a snapshot, we can say that there exists a scenario where the processes could complete their execution and they will not get into the deadlock. We will talk about deadlock in a greater detail in a coming time. Right now I am only trying to discuss about how do I model the resource and process in the system. So, resource allocation graph is one of the technique of modeling the existence of a process and their interrelationship with the resources. I am trying to show you another example where a deadlock is going to be there. So in this case, one can see that what is happening. I have it is the same graph, the earlier graph, except that in earlier case P3 was not making any request for other resources, whereas now in a new graph what we are saying that let us assume that P3 is making request for a resource R2. Now, if you just try to analyze this whole thing, you do not find that now any one of the processes, you can say that P1 is holding R2 and waiting for resource R1, P2 is holding R1 and R2 and waiting for resource R3, P3 is holding R3 and waiting for a resource R2. So, we find that P3 is holding a resource which is for which P3 is holding a resource, P3 is holding a resource and waiting for a resource which is held by P2. So, P2 and P3 can be considered in a deadlock. In similar manner, we can also say that P1 is holding a resource, P1 is holding a resource and waiting for a P2 to release a resource. So, P1 and P2 are in a deadlock, and we should observe one thing here, that we should try observing a cycle. So, let us assume that when we are talking about a cycle, we would follow the arrow direction, and the arrows should move in a one direction. That is in a cycle we call it a cycle if all arrows are in a same direction. So, for an example, we see that we start from a P1. So, from a P1 to R1, R1 to P2, P2 to R3, R3 to P3, P3 to R2, P3 to R2 and R2 to P1. So, we can see that there is a cycle. Please note that this is not a cycle. If I say that P1 to R1, R1 to P2, P2 to R2, and you see that there is no P2 to R2, there is a R2 to P2, the direction of arrow changes. So, this is not a cycle. The cycle is, your cycle is P1 to R1, R1 to P2, P2 to R3, R3 to P3 and P3 to R2 and R2 to P1. This is a one cycle. There exists another cycle as well, P2 to R3, R3 to P3 and P3 to R2. So, we find that there exists a cycle. We have a resource allocation graph, and inside that resource allocation graph there exists a cycle, and this graph we find that the processes P1, P2, P3 are in deadlock. So, we would try to relate the deadlock with the existence of a cycle. So, in this case we are simply making a statement here. We are saying that there exists a cycle and there is a deadlock. This is what we are going to say. We will try to generalize this result. We will try to see that can we say that if whenever there is a cycle there is a deadlock, can we say something like this. this answer, this is a question which we would need to answer. So, we will see that what it is. So, we are trying to indicate. So, just now I posed a question that does a cycle always guarantees that there is a deadlock. So, here we are trying to give you an example where we can very clearly see that there is a cycle. P1 is making a request for a R1, R1 is allocated to P3, P3 is making a request for a R2 and R2 is allocated to P1. And we also see that there are two instances of a R2 and there are two instances of R1. So we have multiple instances of resources in the system. Let us analyze that whether this particular system has a deadlock or not. There exists a cycle. So, if we go by a previous statement that because there is a cycle, there is going to be a deadlock, we would need to check it out that whether the deadlock exists or not. So, let us see that how the things are going to happen. So, we find that this particular system has 4 processes P1, P2, P3, P4. P2 has been allocated resource R1 and P4 has been allocated a resource R2. Now, what happens that P2 does not require any other resource because there are no edges, request edges. So, it does not require any resources. So, because it does not require any resources, P2 will complete its operation in due course of time. Once it completes its operation, it is going to release resource R1. Now, when the resource R1 gets released, this resource can actually be now allocated to the requesting process P1. So, the P1 can get all the resources which it wants. Once R1 is allocated to P1, now P1 wanted 2 resources, that is R1 and R2, and both are allocated. So, P1 will complete. Once P1 completes, P1 can actually release R2 resource, and which can be acquired by P3 and P3 can execute. Even otherwise, if P1 does not execute, it is since P4 is the process which is only requesting a resource R2 which has been allocated. So, it will complete, since it is not requesting any more resource, it will complete. So, it will release the resource, as a consequence P3 will get through. So, even though in this particular graph we find that there is a cycle, but we see that there is no deadlock in the system. So, we would try to summarize certain results which we have observed from a resource allocation graph. So we say that certain basic facts. So, if graph contains no cycle, then there is not going to be a deadlock. That is a fact. If there are no cycles, then there is no deadlock. Actually, we should see that the 4 conditions which we have specified for occurrence of a deadlock, one of the condition is a circular weight, and the cycle in a graph depicts the circular weight. So, if this there is no cycle, then deadlock would not occur. That is, there would be no circular weight, and that essentially means that there would be no deadlock. But if the graph contains a cycle, then we cannot say it with 100% certainty that there is going to be a deadlock or not. It depends. So, there are 2 distinct cases which we can consider. We consider that there are a single instances of the resources in the system, then a cycle would mean a deadlock. But if there are multiple instances of a resources, then there is a possibility of a deadlock. Then we cannot be 100% sure that deadlock is there. There exists a possibility. So we have seen that what the deadlock is, and we have seen how the deadlock can be modeled. How the process and resources are modeled in the system. So we have seen one of the approach, that is we can maintain a kind of a resource allocation graph to keep track of resources and processes and their interrelationship. So so actually and deadlock is something which is undesirable. We can very clearly see that when the deadlock in the system would occur, what happens, that the performance of the system would start degrading, and you can very clearly see that, let's say that two processes, the processes are holding a resources, say process P1 and P2, they are holding resource R1 and R2, and they get into a deadlock. Now what happens? So they are not doing any useful work. Now what happens, that another process comes, P3 process, that also makes a request for a resource R1 which is held by a P1 and P2. Now what happens, that any other process, new process which comes into the system and makes a request for the resources held by deadlock processes, that process also joins the deadlock. As a consequence, what happens, over the period of a time, inside the system, number of processes which are going to be a part of a deadlock are going to become very large, and these processes are in memory. So we can see that eventually when the processes, the set of processes which are in deadlock, that keeps increasing, then the total amount of resources inside the system, they start decreasing, and the system performance starts degrading. All those processes which become part of a deadlock, they don't complete. So overall system performance starts degrading. So some kind of deadlock handling strategy is required. So there are variety of approaches which are studied. So the one approach is that what we do, that we prevent, since we know that there are 4 conditions which are essential for which must hold simultaneously for a deadlock to occur. So if suppose the one approach can be that we prevent the deadlock from occurrence, or so that is a prevention. Then there is something known as avoidance. We would see that what does it mean to say there is a subtle difference between a prevention and avoidance. So we will see that what are the strategies which are there for avoiding the deadlock. Or the third strategy could be that what you do, you don't bother about a prevention and avoidance, and you allow the deadlock to occur, and then once the deadlock occurs, then try to find out a mechanism, detect the deadlock, and then find out a mechanism to recover from the deadlock. So these are the 3 possible approaches which has been studied widely, and we will try to see all the 3 approaches. In this session, what we are going to do is we are going to see the prevention approach, and next session we will talk about avoidance and the process entering into a deadlock and then recovery from the deadlock. So we have seen that deadlocks are characterized by 4 things, that is 4 conditions. It is important that all these 4 conditions must hold simultaneously. We had already discussed about it. So that is these 4 conditions are mutual exclusion, hold and wait, no preemption, and circular wait. So the prevention approach, since it is said that all the 4 conditions must exist simultaneously, so the strategy for preventing the deadlock would be that we try to do something whereby one of these conditions are not allowed to occur in the system. Meaning to say that it could be, we say that okay, avoid mutual exclusion, or avoid hold and wait, avoid preemption, or somehow see that circular wait is avoided. So, any one of them, if we can prevent any one of the condition, if we can design a system where any one of the conditions, these 4 conditions are not allowed to occur in the system, then we know that deadlock can be prevented. So, we will see one by one and see that what it leads to. So, we are saying that to ensure that one of the 4 necessary conditions for a deadlock does not hold, and this would essentially means that we would need to constrain the way requests can be made, can be made for the resources. So we are trying to look at that, can we do something where we say that mutual exclusion in the system is not going to be required. So question which we need to ask is, why mutual exclusion? We require mutual exclusion because there are resources which are non-shareable resources, and there are resources which are shareable resources. So, for our shareable resources, we know that mutual exclusion is not required. So, that resources are taken care of, they would not cause deadlock to occur, since for shareable resource mutual exclusion is not required. But then we have a set of resources which we are saying is non-shareable, and non-shareable resources mutual exclusion is required. So, what can be the approach? What can be the strategy? The strategy is that somehow if we can convert non-shareable resources to shareable resource, then our problem can be solved. So the solution here, if we wish to avoid a mutual exclusion, then we will say that make non-shareable resources shareable. But the problem is that there are resources which are intrinsically non-shareable. One cannot change the nature of the resource. They cannot be made shareable. For an example, printer is intrinsically non-shareable. So we find that it will not be possible in general it will not be possible to convert all non-shareable resource to shareable resource. That essentially means that we cannot avoid mutual exclusion. So then let us look at so since we cannot avoid mutual exclusion, so mutual exclusion is ruled out. Let us now look at that, can we avoid hold and wait? So as a deadlock strategy, so hold and wait, avoiding hold and wait, essentially what we are trying to do here is we are trying to guarantee that whenever a process makes a request for a resource, it is not holding any other resource. That is how it can be avoided, because it is said that the deadlocks occur because there is a process which is holding some resource and waiting for another resource. So if we need to avoid it, then the corollary would be that what we need to do is we don't allow a process to make a request when it is holding other resources. So if this has to be done, then what is required? Then how the processes are going to execute? Processes may require a number of resources. So the one approach can be that the process would be required to request for all the resources which it wants before it begins execution. So in this case, what would happen, that the process would need to know in advance that what are the resources which it is going to require, and it should make all the requests, and it will get allocated all the requests. If the resources are free, it will get allocated those resources at some point of a time. But we can very clearly see that this approach requires that a process should know right in the beginning what are the number of resources which it is going to, what are the resources which it is going to need. Secondly, this could actually lead to a lot of underutilization of the resources. For an example, let us say that I take an example that I say that I am going to read a file from a hard disk, and then I am going to sort it, and then I am going to copy the sorted file on a tape. So now what are the resources which I am looking at? I am looking at a file which is residing on a hard disk. I am looking at a tape and tape. So now what happened that all these resources are granted to me simultaneously. So I have acquired a hard disk, I have acquired the tape drive. Now what happens, till the time the file is being read from the hard disk, the tape drive is unusable, because I would read the entire file and then do a sorting. So sorting also would take some time. While the sorting is taking place, the hard disk is still not released. So hard disk and tape drive both is still held by the process, and when eventually after the sorting of a file, when eventually the file is going to be written onto the tape, at that point of a time what is happening, that file is still held by the process and the hard disk is still held by the process. So we find that it can actually lead to a underutilization of the resources or non-optimal utilization of the resources. So we find this would actually have some problem. So that was one thing, and then the other approach can be if suppose, so we find that one of the approach where we are saying that a process is going to make a request for all the resources right in the beginning. The other approach is that allow a process to request resources only when the process has none. So what happens, that whenever a process requires an additional resource, what we can do, we can say that it will preempt all its, it will release all its resources which it is holding, and then it will make a request. So in this case it would be possible that I acquired 2 resources and then I require the third resource, and when I am trying to going to make a request for a third resource. So what I am required to do as per this protocol is that release the 2 resources which I am holding and now make a request for 3 resources, and it may just happen that these 3 resources may not be available at that point of time. So we can see that this would lead to a low resource utilization, and this can also lead to a starvation. It may just happen that every time when I am requesting, going to incrementally make a request for another resource, I would release a resource, and when I make a request once again, I don't get that resource. So every time incrementally a resource allocation is carried out, and when I try to make a request for another resource, I release. So I get through this cycle, and I find that the process could starve for the resource. So we have seen that the second approach also, that hold and wait cannot be completely avoided, cannot be eliminated because of the issues involved there. So now let us try to see that if we can relax the condition of a no preemption, that is, we allow the preemption to take place in the system. So in this case we are saying that if a process that is holding some resource and it requests another resource that cannot be immediately allocated to it, then all currently held resources are released. So, for releasing the resource, what is required? That we are preempting the resource. So, we are trying to create a new protocol here. We are saying that this is how it should work. So if that is that is the approach if we need to follow, then the steps which we need to do is going to be that preempted resources are added to the list of resources for which process is waiting, and then process will restart only when it can regain its old resources as well as new resources. So in this case, the number one, the preemption has a problem. Certain resources which are certain resources like printers, etc., printers, tape drives cannot be preempted, because once it is allocated to a particular process and the process has started using it, it cannot be preempted in between. So there is a problem. So allowing preemption is a problematic thing. We find that it is for certain devices this is not going to be possible. There is another. So this is a kind of a approach which can be or a kind of a protocol which can be thought of if one is going to allow the preemption. So I am saying that the system would check if resource is available. If the resource is available, then there is no issue. It can be allocated to the process. So you will go through this branch and allocate the resource to the requesting process. If the resource is not available, then what are the possibility? The possibility is that resource is allocated to a waiting process. There is a possibility that resource is allocated to a waiting process. So if it is allocated to a waiting process, then that resource should be preempted from the waiting process. Preempt the resource from the waiting process. If resource is not allocated to the waiting process, then this essentially means that resource is being used by the process which is an executing process. So probably this resource will get released at some point of a time, and then it can be made available to the requesting process. So as a consequence, if the resource is not allocated to a waiting process, then in that case the requesting process should be made to wait. That is, it can be suspended and it can be made to wait. It can go into a blocked state and can be made to wait. So this is a kind of preemption strategy which one can adapt to, but we know that certain resources cannot be preempted. So this approach also we find that cannot be utilized. Finally, so we find that out of four conditions, 3 conditions, we are unable to relax those 3 conditions. So now let us look at the last condition, and that is a circular wait. So the one of the proposed protocol was that impose a total ordering of all resource types, and these resources are assigned some kind of a number, and the resource request is always can be either in an increasing order of enumeration or can be in decreasing order of enumeration. So some kind of order can be maintained. So it is essentially that if I say that a system has a resources say 1, 2, 3. So if a process has made a request for a resource type 1 and resource type 2, resource type 3, and now if this process wants to make a request for a resource type 0, it will not be allowed. So it can only be allowed So this will essentially mean that in previous case we had seen that process P0 was process P0 was trying to make a request for R1 which was held by P1, and P1 was waiting for a P2, and Pn was waiting for P0. So if such a strategy is adopted, then in that case we can say that Pn will never wait for P0, because we are saying that resources have to be accessed in a increasing order of their enumeration. So this would actually break the deadlock, but then this essentially means that resources, there has to be a strict resource ordering, which is not a very easy task. We cannot say that hard disk is going to be 1 and keyboard is going to be 2 and tape drive is going to be 3 and so on so forth. So eventually we find that the attempt to prevent the deadlock by avoiding the 4 required characteristics does not bear any fruit, and it is not it has a lot of problems associated. Therefore, it is safely concluded that a deadlock prevention cannot be carried out in the system. So we would stop here in this session, and next session on a deadlock prevention, we are going to talk about a deadlock avoidance, and we are also going to talk about a strategy where we allow the deadlock to occur and then try to recover from the deadlock. So we will try to see these things in a next session. Thank you.